the slides. Perfect. I'm going to keep it like this because we're going to be hopping on and off the slides from now, from time to time, just to get a bit more practical. But yeah, thanks for the introduction. So actually, really briefly about myself. This is my channel on YouTube, and I come from a computer science background, and basically got into quantum computing a while ago. And basically, that's the way I decided to approach the learning journey, is by creating an exploration channel where I would just, go and record myself, reproducing papers and learning about new models and exploring things about quantum machine learning and stuff like that. So everything that we'll be talking about today, like the goal for today is really not to give you something really concrete in terms of expertise, but to give you some sort of overview so you can go out and explore by yourself, because I think this is what's the most fruitful for such a topic, which is really, it's a new topic that it's also growing, big and really fast, and so it's difficult to with the time given deep dive into something, or get like enough expertise on some concrete topic, or even on the overall thing. So we're going to be focusing on these. Feel free to go there, browse the channel, and maybe what I will do now quickly, because I don't know how much familiar with quantum computing the audience is. I'll do a quick primer, just so just to motivate the rest of the presentation as well. And I'm not going to follow any other standard introductions of bits and qubits, but I'll rather be practical and hop into this tool, which is the tool is called Quirk, and it's a quantum computing simulator built by Craig Gibney, who is working at the Google quantum team. And this tool is something he built before he joined Google, obviously, and he poured a lot of effort into this. It's a tool that allows us to take a look at quantum circuits, which are basically, at the moment, currently the first-class citizen of how you interact with a quantum computer. And they allow you to do this in a really comfortable way, in a really quick way. And you can also take a look at how the circuit and how the quantum state evolves in there, right? So, but just very quickly, for those who are not familiar with quantum computing, what we have here, instead of bits, are quantum bits, so qubits, and those are these represented by these wires in here, right? So we have 2 wires right now here, and you can have more, obviously. The circuit allows you to, and the tool allows you to place gates and have more qubits in here. There's a limit to how many qubits you can have, because as you can see, a circuit with 4 wires has a state representation that is like 2 to the power of 4, right? So it grows exponentially. It's 2 to the power of the number of qubits, and so if if we keep forcing the thing, at some point, I mean, I think in the browser you can simulate up to 16 qubits. Some of the biggest simulators out there can do about like 20, 30 qubits. But basically, the idea is you cannot like simulate more than these, because that's the idea of quantum computing. That's sort of the one of the main points of quantum computing, is that that's going to give you the advantage, right? That you can simulate, you can have so much working space, so to say. But basically, that's what you have. So you have 2 components, right? Like each qubit can have, each qubit is represented by a ket, which is basically this 0 here in between brackets. This just means it's in the state 0, but instead of being like a classical bit that it can be a 1 or a 0, this qubit can be in any linear combination of those numbers, right? And you can see this little sphere in here. It's called the block sphere. It's a way to represent the state of a single qubit. So 0, it's usually represented with the block sphere pointing up. So every point in the sphere is a possible state of the qubit, right? So if we apply a NOT, like an X gate, which is the equivalent of a NOT gate, what it does is it flips the state to the bottom, which is the state 1, and here this marks it as on instead of off. But you can also do something beautiful, which is you can apply a gate called Hadamard gate, which what it does is it stays between 0 and 1. So what we call this is it's created a superposition, and so this display here shows you what's the state of this qubit in a wave function representation, right? So not in a block sphere, but in a box which has two squares, one for the component of 0, another one for the component of 1, and you can see that. Let's see if I can zoom in actually a bit. You can see that the amplitude of 0, that's what we call it's the value associated with 0. It's a complex number. It's 0.7 plus, 0.7 real in this case. It doesn't have any imaginary component, and the amplitude of 1 is 0.7. So basically, the way that you calculate the probabilities of measuring each qubit, because what you have to do with a qubit is, at the end of the day, you have to measure it to know what is the real value behind this. You have to it's what people call collapse the qubit. It's the square of each of these amplitudes. So you have, and as you can see already, what this leads to is that the more that you use this gate, the bigger. Like this is the box that represents your full system state. So a system with 4 qubits is going to have amplitudes for all the possible combinations of these 4 qubits. You can see here the amplitude for 0, 0, 0, 0, and you can see here the amplitude for 1, 1, 1, 1, and everything in between, right? And that is just one dimension of the whole thing. So the other thing you can do with these is you can play with what's called the relative phases of these qubits. So a 0, we'll go back to the case of 1 qubit. In here, you see that we have those circles in here. Those circles represent what's called the phase of a qubit. So it's basically, or the phase of that particular amplitude. So what you can do is you can apply a Z gate, and what this does is it flips this phase from being 0 degrees to being 180 degrees. You can see this at the bottom of the tooltip. And what this essentially has done, if you take a look at the value of the amplitude, it has negated the value. It's minus 0.7, and this is 0.7, right, plus. And so this is where the next advantage of quantum computing comes in, which is, or one of the next tools that you can use in quantum computing comes in, which is called interference, that makes it different than any traditional computing model, is that you can play with these, so these probabilities, these amplitudes cancel out, right? So, and I'll show you how this looks like. So if you have a Hadamard gate, right, it takes you from the state 0 to the state 0 plus 1. So you're in between 0 and 1, 50% chances of measuring 0 or measuring 1. If I would apply the Hadamard gate again, it's a gate that it's its own inverse, and so when I apply this gate, it basically goes back to the starting point, right? Now, an interesting feature of the Hadamard gate is that if it acts on a qubit that's in the state 1, instead of going to the state 0 plus 1, it goes to the state 0 minus 1, right? So it's simply because what the Hadamard gate is doing. If you think about the how this would look like in this block sphere, it's rotating along the in the middle of the two axes. So it's not rotating. Let me show you if I can show you a bigger block sphere. So we call these axes at the top, like this axis is the z-axis, and then we have the x-axis and the y-axis. And so the Hadamard is doing is just rotating in between the x and the z-axis in a way that if you're at the 0 state, it's going to rotate and end up in this state in here. But if you're in the 1 state, it's going to rotate from the back and end up in that part up here. So now the beauty of interference is that you can manipulate these phases independently, right? So you can say, now that I'm in this state, I want to apply the Z gate, which, remember, it was negating the phase. So now we are going from a minus to a plus, right? And if I now apply a Hadamard gate again, instead of coming back to 1, I come back to 0. And this is what's called interference. So you've basically created, let me see if I can also show you better in a simple notepad editor, right? So we've moved from, and I'm going to simplify the notation. So we've moved from the state 0 to the state 0 plus 1, right? And now applying the Hadamard to the state 0 plus 1, it's like applying the Hadamard to each of its components, right? So you have, you know, you have a 0 plus 1, and we said that the Hadamard applied to the 1 state, it gives you a 0 minus 1, right? This is why when we apply another Hadamard here, we saw without the Z, we're going back to the original state. It's because these two amplitudes that correspond to the one component cancel out because it's a plus 1 and a minus 1, so we end up just with the 0. And this is an important notion to understand in quantum computing, because we will see that one of the problems, one of the challenges that we have is that, yeah, you can have a really big space, a really big computational space, but if my solution is somewhere in here, how am I supposed to to be able to read the solution? Because, well, if I want to read these, and this is a simulator so you can see what it looks like, but if you're really playing with an actual quantum computer, you have something that's just too big, and so you cannot see what all the amplitudes are because you have an exponential amount of them, and so you need to measure the qubit the circuit multiple times. And when you do the circuit readings multiple times, every time you're only going to get one of those components. And what you have to do with time is you have to build up we have to sample the distribution and get basically those values, right? So it's going to be basically, it's going to kill your quantum advantage, because if you've managed to solve a problem within this space, but you cannot read the solution, and the only way to read the solution is to sample 2 to the power of n times, then it's not there's no advantage anymore. So that's the idea. And so this is, I think, just the very basics of these. So you have, as I said, just a quick recap, you have multiple gates in here that you can play with. The X gate, you have the Y gate, the Z gate. They all have their own different effects, and if you like thinking about this mathematically, each of these gates corresponds to a unitary matrix. And so at the end of the day, the math, like the simulation of a circuit, is really just a matrix multiplication, right? So your state is represented by like a vertical vector, and these are matrices. So basically, this circuit is equivalent to saying, the matrix for X dot product the vector for 0, right? And that gives you the state of this whole thing. And then you have a bunch of other gates in here that are like square roots of other gates. For example, you have, if we go to the Hadamard gate and you apply like an S gate, what the S gate does is it takes you into the complex numbers, right? So it takes you not from like 0 degrees to 180 degrees, but it stays in the middle. And basically now, if you take a look at the amplitudes of these, you will see that the value has got like a complex component. So it's not anymore purely real. And this is important because this can also help you with designing interference patterns. But so we talked a little bit about these. Then another thing important to know about quantum computing in terms of the basics is the notion of entanglement. So what you can do here, now you might think, okay, so but so far I've been touching individual qubits. So what happens when how can I interact with more than one qubit, and what's the effect, right? So you have what we call the controls, and what you can do is you can say, look, I want to have a controlled X operation. So if the control qubit is 0, I don't want this X gate to be executed, but if the control qubit is 1, I want this X gate to be executed, right? And so now we have a circuit that's in the circuit that's in the 1-1 state. Now, the beauty of this is what happens if the control qubit is in superposition. What happens if the control qubit is in the 0+1 state? Well, we get an entangled state, which means that, and this is really important, which means that like the value that you're going to measure for the second qubit, it's fully correlated with the value of the first qubit. But if you measure them independently, you've got 50% chances. Like remember, the Hadamard gate was taking you into the 50% realm of whether you're going to measure 0 or 1. But we know that if we measure 1, right? And I'm going to use these gates in here, which are special types of gates which tell the simulator, pretend that I've measured a 1, right? If I measure, pretend that I measure a 1 in here, you see that immediately the second qubit state, which was also 50% chance of measuring 0 or 1, collapses to also being 1, right? Because we know now that this qubit was 1, and therefore the control node must have been like executed, right? So this is the this concept is a concept that's really important because it helps us implement algorithms that help us transfer information, not information, but helps us basically encode algorithms in ways that you cannot do classically. And it's also the basis for some interesting cryptography. And it's just, you know, it's really interesting to see, you know, these kind of effects. And the same happens here, right? If you measure this one, you instantly know what the other one is. Now, some of you might have heard about quantum teleportation. Let's see if I can actually show you, because Quirk has some built-in circuits in here. So this is a circuit that basically what it does is it teletransports a state that's in this top qubit to the bottom qubit, and it's using entanglement, as you can see as well, right? And a lot of, you know, some people, you might read on the internet that this means faster than light communication, but it's definitely not the case, because as you can see, in order to understand and to decode this qubit, you need to do some, you know, if this is Alice and at the top and this is Bob at the bottom, Alice and Bob need to communicate the results of the measurements so that Bob can correct his qubit. I think that's it. I don't want to, you know, lose too much time with these, but the idea is, I also recommend, I have a page called uncertainsystems.com, uncertain-systems.com, where you can go and actually, if you're new to this, you can also, you know, play with some puzzles. I've built some puzzles here that help you build up intuition, you know, for the very basics. So when you have a puzzle in here, it's a version of Quirk that doesn't show you everything, and the goal is to turn all the qubits off. So you have to play with the gates, and you know, you practice. It's a bit of a dojo. So you practice by means of doing puzzles, and it gets more complicated until you can go. I'm still working on it, but until you can go to level 10, and you have like something like Grover's algorithm, which is a more complicated algorithm, and it's broken, and the goal of the puzzle is to fix the algorithm. So yeah, this is something that you can do, and I think it's a fun way to learn. But let's go back to the presentation. I hope I've been we'll go back hopping on and off this tool, because we're gonna try to use it to understand some of the things that we're gonna be talking about. So that's yeah, that's what I said. So these uncertain systems, but now let's get into quantum computing meets machine learning, right? And probably most of you, or some of you, if you were not aware of quantum computing before, you might think, well, this is great, right? Like, this is great for big data. This is great because it looks like you've got free parallelism, right? Because, I mean, maybe it was not obvious, but let's imagine we built a superposition that's like, you know, pretty big. So I'm going to be moving these things here. What's really interesting about, you know, having a superposition like this is that, for example, you can play with, you can interact with these qubits, right? And for example, say, you know, look, if I do, maybe let's do it differently, right? So let's make a simple example. So if you have something like this, like you can build interesting logic, like using a multi-control gate to move elements around your space, right? So if I take a look at this, before the NOT gate, we had this state in the system, but now what we told the system is, if these three elements are all one, because that's the control is black, meaning if these elements are all on, turn and flip this qubit from 0 to 1. And so basically what this has done in all our states of possibilities is it has moved this one away, right? So you can imagine that you can use this to implement some sort of arithmetic as well, because, well, basically, what you can do is you can do something like this, right? You can say, look, this. Let's imagine my first 2 qubits are like the input register, right? So it's a 0 or 1, and I want to build like a half adder or something like this, right? So what you can do is you can do something like that and say, if this is 1, right, then flip this 1 to 1, right? If this is 1, flip this 1 to 1 as well. And if these 2 are like on, then you kind of have like a bit of it's not totally correct, but you get what I mean, right? So you can actually build operations in superposition, and this is something that you might think like, well, it's like free parallelism, right? I can do a lot of, and I can maybe speed up a lot of the things that we use in machine learning and stuff like that. And also one might think that it's also a really interesting tool for modeling, right? You can maybe use these states as some sort of model, so you can map maybe you can map your data somehow, load it into the qubits, and then play with the fact that you can parameterize gates, right? So for example, what you can do is you can say, dear circuit, I want to have this one. I want to have I'm going to use this here. So I want to have I want to have this gate, which is dependent on a parameter, right? And this parameter can be, for example, I give you the value of like 1/2. And so now this is going to do a half of an X gate, right? But I can also say, just do a 1/4, right? And so you can parameterize these gates, and you can think that, well, that's interesting, right? Because you can basically plug this into a classical computer and say, look, if this is my parameter, right? I can try to train these and use the circuit as some sort of neural network, right? Because at the end of the day, as we said, the gates in the circuit are equivalent to matrix multiplications. So this is really similar to what you would find like in a neural network. So the idea is, you can have these parameters and you can have multiple parameters. So you can maybe, it seems like you might have like a much more powerful modeling tool in here, because your state space is really big. It grows exponentially, right? So and these are common myths really in the industry. But we'll see now that this is not that easy, right? So the first problem that we encounter, and you should always take a look at quantum machine learning algorithms and papers. Output problem, right? So, and I have linked a video. In order to do your algorithm, you have to load the data into the circuit, right? Because the circuits always start with the 0 state. So you have to have a portion of your circuit that prepares the data. So let's imagine that you have a vector, an array of data of numbers between 0 and 100, and you just want to load them, right? There's different strategies you can use. You can think of saying, well, if my state has 4 elements, then I can encode 4 data points in here. And that might be tempting, because you think like, well, this means that in 2 qubits, in 2 qubits, I actually have I can encode 4 pieces of data. You can actually encode a little bit more. The truth is that the encoding mechanism is really going to cost you as much as the amount of data you have. So that's why it's always important when you read about a quantum machine learning algorithm that you understand that it's the fact that like a lot of the algorithms depend on something like a quantum RAM existing, which doesn't exist yet, which is a concept of a mechanism to load data in a quantum computer efficiently, right? Because if you do it the dummy way, like just by saying, then I'm going to load this one in here, then I'm going to like do something else and build a, or maybe maybe I'm going to build it in the phases, right? So I'm going to build a superposition, and I'm going to do something like, look, now for this element. So for this element in here, I'm going to rotate 90 degrees. For the element 0, 1, I'm going to rotate like a bit less. So you can see that I'm actually really encoding data in there, right? I don't know, I will use maybe another, the S and the T gates are just sort of versions of the Z gate, but I can use like these, for example. So like all what you're saying is you're encoding in each element, but as you can see, I have to build a gate per element that I'm encoding, and so that doesn't feel like efficient, right? And it would basically kill. It would kill any speed up that you might think you're gaining, and that's really just a stupid example, but like just so you understand that. And then obviously the other problem that we talked about already is the output problem, right? So if you have a huge state and you're only interested in one particular solution, for example, you've done your algorithm and you're interested in knowing, what's the element that has, whatever the biggest number in the upper register that it's made out of these like 3 last qubits, right? Everything. You would have to really measure. Every time you measure, it's important to understand that you get a random element from this collection. And so in the worst case scenario, you really have to sample as many times as many elements there are for you to even know whether there's a solution to your problem that you can read. Now, the beauty of this is that if you don't need the solution right away classically, you can still, like the advantage here is that you can still use these kind of results within your quantum circuit. Right, so you can now maybe connect your, quantum PCA result to the next step in your pipeline. Just because everything happens inside the quantum computer, you don't need to take the value out. It's still there. You can still access it in theory, but you're not you don't have to take it out. That's a solution to this. But at the end of the day, if you're not able to create an interference pattern that eliminates values which are not correct ones, then you're not going to be able to measure these. Right. So, and so you always have to, it's preparing the data kills the speed up, reading out the data kills the speed up. And then even if we would have a quantum RAM concept, which is, it's a really interesting concept if you think about it. So let's see if I can show you the animation that's there. So it's, there's an actual paper like that. It really kind of, goes and explains, some of the details of how you would implement that, right? But the idea is that you would really have sort of nodes that like you could load data into superposition, right? So the idea is you would have, you would be able to load, for example, 3 elements directly into your circuit in superposition, but it's not, it's not cheap, right? So that's the point. And if you think about one element which I avoided at the beginning to talk about, which is that quantum qubits are really unstable. They're really, these are really implemented in many different ways. Sometimes it's like you've got like cold atoms, you've got like trapped ions, you've got like superconducting qubits, and those have to be operated at really, the current machines that exist, they have to be operated at really low temperatures in really well isolated environments so that the noise of the environment does not destroy the quantum effects that happen inside the computer. And this means that to do error correction in those, because at the end of the day, the only path to a fully scalable quantum computer would be to have qubits that are error corrected, so safe from errors. It would just require too much computational power to error correct these, which kind of would I think really quickly diminish the advantage in comparison to like a classical machine learning algorithm. And by classical, I mean a non-quantum one. So this is something important to know. And another interesting thing to know is that in terms of the modeling, right, is that for classical data, it is really difficult to beat a classical neural network. So this is really interesting example that I recommend everyone, to go take a look at from TensorFlow. TensorFlow has released, they've released their integration with Cirq, which is Google's circuit language. And basically they have some really interesting tutorials in here that I recommend everyone who wants to learn about this to go through. And they make a really good case of, they try to do the MNIST train like a quantum neural network for the MNIST data set. And at the end of the day, they compare, so they compare the results, right, of the quantum classifier, the classical classifier using the full data set, and a classical fair. They call it fair because obviously there are too many data points in here for a current simulator is not able to encode as many data points, right? It would be too many qubits. And so they do what they do is they do some dimensionality reduction. They smoosh a bit the image, and and they also do a classical version of the smoosh training just to compare, and it's still slightly better than the quantum one, right? The point being that the way that you train a quantum neural network is really based on the average of the distribution that you're creating, right? So if you have if you think about this as being your distribution, the only one of the ways that you can do some sort of derivation on these, so you can actually move your you can fine-tune your parameters correctly, is that you can only take a look at the expectation value, which is basically the average of your measurements, and then this allows you and allows your circuit to be differentiable, but only because of these you can, or thanks to these, you can differentiate it in the same way that you do with like the typical sinus or cosinus function, with just a linear combination of the measurement of the circuit, but with a shifted parameter. So you have the what's called the parameter shift rule, which there's basically actually, by the way, really good resources here. And Penny Lane is another quantum computing company that they have tons of resources for learners that want to get into these. So thanks to what I just said, like you can basically calculate the derivative of a circuit with respect to a parameter by just doing the subtraction of a shifted version of the parameter, just because of the way that the quantum gates have this kind of circular and repetitive pattern, right? And so because of these, the way that you can train these nets is not as accurate as a classical, especially for classical data. What you're doing is you're just encoding classical data in the system and trying to do this. You're not going to get the same type of accuracy. Now, for quantum data, this becomes more interesting, right? So what happens when you want to, I don't know, simulate or model like a chemical compound, or like even just smaller, just like something within chemistry, whatever, something that kind of has, you have to model electrons and you have to model the spins of the electrons. Basically, you have to model things which in and of, by themselves are quantum systems in nature. Then this is when you can really take advantage of this tool. And yeah, so this is an important thing it's definitely an important thing to keep in mind. The input and the output, and basically the accuracy of these things is not always obvious, and it's not always better than classical. Now, the reality is, that you have sort of two ways to use a quantum computer or a QPU, or like a quantum computing unit nowadays, right? And of course, this is not definitely everything. There's a lot of, cutting edge research being done on different ideas. But in general, these are the two concepts that are the most well established right now, which is on one end, a circuit as a model, as I said, of course, with the caveat that that this is more thought, it's more thought to be used for quantum data and quantum problems, right? And I can give you an actual more concrete example of these. Is the problem of finding a ground state of a Hamiltonian, a ground state of a system. It's basically something that you can solve with having a circuit as a model, in the sense that you start the circuit, you fine-tune the parameters, and the beauty is that the expectation value, the average of your measurement, right, is basically there's a lot of math behind this, but it's basically an upper bound to the ground state energy of your system. And so if you find a way to minimize the expectation value of your circuit, then you're approaching the ground state of the system. And so after doing, you know, some classical optimization outside of your circuit, you can fine tune the parameters and really find something close to the ground state of the stuff you're simulating. So this is one of the things you can do. And then, of course, you can use the quantum circuit as an accelerator, right? To be honest, it's kind of fun because it's a bit like the same that was done with GPUs, right? Where people realize, well, a GPU has a much more efficient matrix multiplication mechanism just because it was thought for graphics. A QPU is a bit the same. Actually, as I said, the gates are at the end of the day matrix being multiplied with the state representations, and so you can, in theory, in some cases, find ways to use these to speed up multiplication of big matrices, right? And here you have a list of algorithms that I'll definitely, you know, I definitely recommend that you go and take a look at. We're not going to get into each of the details, but I can talk a little bit about them. So you've got basically, you know, your typical quantum PC, like quantum versions of things that already exist, right? So PCA, support vector machines. Now the quantum version basically relies on, you know, kind of operating on superposition, for example, for support vector machines, right? So you're calculating the difference of you're calculating the kernels really in superposition, and so what you're doing is you kind of have a more you're parallelizing that a bit more, right? With HHL, it's a new algorithm. It's not new. I mean, it was already invented quite some years ago. But the idea of this algorithm is that you can solve linear systems of equations, because basically a linear system of equations is nothing else than just like a big matrix, right, multiplied by your array of variables and equal to your array of solutions, of vector of solutions, and that kind of gives you, if you can encode your linear system of equations into a big matrix, and then you can put you can somehow load this big matrix into a quantum computer. This algorithm gives you a recipe to actually solve these. But again, it doesn't really solve it in a way that it's you don't get the right solution. You get an approximated solution, and you know it only works under certain conditions. In case, you know, only if the matrix is really sparse, and it doesn't always work. It has to also be invertible. There's a bunch of, you know, technical details you have to consider, but for some small cases, this could work, right? And you can see that, like, these really has the shape of a matrix if you know, lay it out this way, right? And those are the different elements that have value. So if you're able to encode your matrix in here, which is not always possible directly because these matrices must follow certain rules, then you can use to your advantage. Then you have annealing. We haven't talked about annealing. We haven't talked about annealing yet because it's a bit of a different model. So I don't know if you know D-wave systems. So it's actually, I think, the only quantum annealer out there commercially available. So, you know, we talked about quantum computers having or being able to simulate like a bunch of qubits, and real quantum computers, like the biggest quantum computers out there, I think they are not above 60 or 70 qubits, right? Now, these guys have a quantum computer, well, a quantum annealer to be concrete, that, like, the recent one they've released, it's called Advantage. It has 5,000 qubits, but it's a bit of a different beast, right? So it's not this gate model. It's not about, like, you cannot program it this way. The only way that you can program this system is by the system is supposed to implement something that's called annealing, or simulate something that's called annealing, which is basically you prepare your Hamiltonian, you prepare like your system state, a system state that you know about, for example, an equal superposition. And let me see if I find the actual, because they have really interesting. We can take a look at this later, but like they have, so you prepare the state and then you let the state evolve with time towards another Hamiltonian that's your target Hamiltonian. Now, what the quantum mechanics tells us is that if you have such a system where you're evolving your system towards another one, and you do this slow enough, your ground state stays all the time the same, and so you're able to basically measure at the end, like you know, a solution to a to sort of an optimization problem, so to say. If you are able to encode your problem into a quadratic, so a cubomatrix, right? Then you can give it to the quantum computer, and it will actually solve the problem for you. And actually, it does a really good job. It really does a good job. So if you can encode your problem, you know, in this way, then you can give it to. But it's a different beast. Now, the caveat here is that it's not always straightforward to do this, and it's still, there's no formal proof that that this type of computation really brings any true advantage. So it's a bit of a, you know, it's probably too early to really, you know, be too excited about this, but it's definitely something interesting to play with. And yeah, and I think I stretched my time almost already to the very end for 45 minutes. It's just, there's too much to talk about. In this case, it's difficult to, you know, compact everything to a short presentation, but I definitely recommend that you take a look at least Penny Lane when you have a lot of resources on quantum machine learning. If you're interested in learning more about these, and they have a lot of practical stuff as well in here that you can play with, not just these, but like you have you know, interactive demos, you have like glossaries, and you know, you can, you know, even go through the basics and understand and, you know, build small simulations. And these guys also have even a different quantum computer, which is basically based on photonics quantum computing, and so that's also a different beast. But so that's one thing. And then I also recommend go to the TensorFlow quantum library, because there's also a set of really interesting tutorials in there to follow. Yeah, so that really covers everything that I wanted to cover in the presentation today. Just, you know, a rough view on the field. It's much deeper than these. I just wanted to make sure, you know, my goal here was to basically transmit or give you sort of the basic tool set to go out and explore by yourself. You know, keeping in mind what are the caveats for typical quantum machine learning hype stuff that you can find out there. And you know, feel free to come and visit the channel as well. There's a bunch of other videos, not only quantum machine learning, but also quantum machine or quantum computing fundamentals, which, you know, I'm exploring live on the channel. This is not your typical 10-minute video type of thing, right? So those are like long videos, 1 hour, 2 hours, where I do like really hands-on sessions exploring stuff. And so you kind of see my learning journey full end-to-end with all the ums and ums and getting stuck and all that stuff, just because I want to transmit that full journey as well and make it public. Good. So